This video presentation is titled X6417 Test Process, and it will focus in providing a recording of the final test process performed to the X6417 generator as part of the manufacturing acceptance test procedure carried in the Mexico location of Spellman High Voltage Electronics Corp. As a brief introduction, the X6417 is a 50 kilovolts, 100-watt micro-X-HP generator for X-ray applications. It consists of a high-voltage output that connects to the X-ray tube anode and a filament current supply that drives the X-ray tube filament. Production tests focus around testing the generator for arc survival, accuracy, regulation, safety circuits, self-diagnosis, tube operation, and other specifications. The tests performed in this video are contained in the Spellman High Voltage Test Procedure number 100-961-436, which outlines testing carried specifically for X6417, including the final test shown in this video. In general, the final test performed can be divided into 4 different sections, which are output arc or short circuit tests, where the high voltage output is shorted several times to ensure the robustness of the generator. The manual interface test, which tests for the analog control, regulation, and compliance to outline specifications. The computer interface test, that confirms functionality of the serial, USB, and Ethernet interface, as well as GUA reading accuracy and self-diagnosis functions. And last, but not least, the X-ray tube test, which is done to verify the performance of the emission loop under the final application. Final test begins with the arc testing, and the configuration is the one shown in the video. It can be observed that the generator is disconnected from a majority of the measurement equipment with the exception of the DMM protection box, which is intended to protect the equipment during arcing event. A ground stick is used to short-circuit the output directly while the generator provides full rated output. As shown in the test demonstration, you can notice equipment is disconnected from the X6417, with the exception of the ones in the DMM box. All meters are turned off. You can also see in the high voltage section of the test setup that contains the load and high voltage divider to which the X6417 connects through a high voltage cable. For this test, as you could previously see, the ripple checker, which is a DC blocking high voltage capacitor for ripple measurement, is disconnected and grounded for protection. Input 24 volts DC power supply will be powered up, and as per the connection diagram shown, once 24 volt input is enabled and X6417 is confirmed to have the high voltage LED in the on condition. Unit will ramp to the maximum output voltage and output current. As seen in the screen, output voltage reading is 50 kilovolts, while output current reading is 2 milliamps. Output voltage readings come from a 10,000 to 1 high voltage divider tab. Hence, 5 volts in this meter are representative of 50 kilovolts. We will proceed to engage the DMM box protection again and begin with the actual shorting of the output. We will approach the ground stick, which is an insulated rod connected to ground to the high voltage divider dome, performing 10 shorts to the output at a frequency of 1 short per second. After the arc testing has been completed, arc testing passing is recorded in the datasheet and test setup is configured for the following tests. The test setup now being shown is meant for the manual setup testing, which is done through the help of an analog interface test fixture connected to the 15-pin connector of the X6417. During this test, the test fixture and load are changed in various configurations for testing for accuracy, regulation, and other specified characteristics. As you can notice in the video, the test fixture is connected to the 15-pin connector. In addition, a 1 ohm filament load can also be seen connected to the filament output to perform filament testing. This is connected to a calibrated current meter. A 6.5-digit calibrated DMM is also used for test point readings required through the test process. As mentioned in the previous ARC test, the output voltage and output current meters are hooked up to the output of the 10,000 to 1 tap of the high voltage divider and the current return respectively. Calibrated input power supply can also be seen in the screen. We will also be using a calibrated oscilloscope for output ripple and rise time measurements. In the high voltage side of the setup, you will also notice that the ripple checker for ripple measurements is now connected. Here you'll be able to have a closer look to the high voltage test setup. Ripple checker and high voltage divider are calibrated instruments. You will also notice that the current return path of the high voltage divider and the load are tied together, and the sum of those currents is measured at the current meter. Reason for this is that the HVD current is not negligible and needs to be considered to ensure an accurate calibration. Testing will begin with the output voltage and output current accuracy verification, where we will compare the output voltage and current to their respective programming and monitor signals. You should be able to tell from the image that the meter configuration is as outlined previously, with the output meters being in the same position. The filament output connected to the calibrated current meter through a 1 ohm load, and the test point meter to obtain test point data. It is important to remember that the configuration dip switch labeled as SW1 should be in the configuration shown to enable interaction through the analog interface instead of the computer interface. High voltage output is then enabled via the analog test fixture as seen now in the video. The fixture contains a switch in series with a 270 ohm resistor connected between pins 4 and 15 of the 15-pin connector. Max output voltage and current are now present at the output. DMM will be reading the maximum programming voltage at pin 7 of the 15-pin connector, provided by the Micro X local control, which is tied to the internal precision 10-volt reference. Programming voltage will then be lowered to half scale, which is 5 volts of programming with a tolerance of plus or minus 50 millivolts. Once the value achieved is as centered as possible, the voltage monitor test point will be measured, where we are confirming that the monitor signal is 5.009 volts at 25.11 kilovolts, both which are under specification. Value is then registered to the test data sheet. After that, output voltage is adjusted to achieve 1 milliamp of output current. Value in the DMM is centered as much as possible. In this case, to 1.000 milliamps. After the current value is achieved, The test point DMM is used to measure the voltage at TP7 of the Micro-X control board. Reason for measuring at TP7 and not in the 15-pin connector is because the current monitor signal that goes to the 15-pin connector is not available unless operating under X-ray tube. This will be performed later. It can be seen that 4.990 volts are reached in the current monitor signal at 1 milliamp. Value is recorded in the datasheet, and we can proceed to the next test. Next test is the dropout test, where the applied 24-volt input voltage is decreased until either the unit stops regulating or input voltage constraints internally set for the undervoltage fault are reached. This value should be below 22.7 volts. We will decrease to 23 volts input and then begin decreasing in steps of 100 millivolts until that condition is achieved. As noticed, unit maintains regulation even at lower than 22.7 volts, being able to operate down to the undervoltage fault limit threshold without losing regulation. Since the unit lost regulation at 19.1 volts due to reaching the undervoltage fault, this will be recorded as the dropout voltage. After the fault has been issued, power is recycled to allow the unit to turn on again. Unit is set to maximum rated voltage again, including maximum filament and input current is recorded, ensuring input current remains less than 7.75 A. In this case, input current is 5.81 amps, which is within specification. Value is recorded into the datasheet before proceeding with the next tests. For the next test, the output voltage adjustment range is verified. Programming voltage test point is measured while the output voltage is increased to maximum value and decreased to minimum to confirm full adjustment range between 0 volts and 50 kilovolts. It can be seen that programming can be changed between 0 and the maximum programming voltage, and the output can change between 0 and 50 kilovolts. Range is recorded in the datasheet. In this following test, a lower value resistance load of 10 mega ohms is connected to the output. This is in order to test the X6417 current limit. With the output still set to 50 kV, unit will be powered up. Unit should limit the output such that the output current does not go past 2.2 milliamperes. it can be seen that even with the output set to 50 kV, the output voltage limited to a lower value to ensure current did not exceed 2.2 milliamperes. Value of the current limit is recorded into the datasheet. Next tests to be performed are the line and load regulation tests. The unit is configured again to full rated output as seen in the screen. Then the input voltage is lowered to 23 volts and the output voltage differential between 23 volts of input and 25 volts of input is measured. This should be less than 5 volts. In this case, the voltage differential reading given by the relative measurement function of the DMM is 1.2 volts, which is within specification. After this, line is set to the nominal value, and load regulation test is performed by measuring the voltage differential at the output at full load versus no load. This should be less than 30 volts. In this case, both reading from no load to full load and full load to no load are 27 volts, which is within specification. The following test is the ripple test. For this, a calibrated oscilloscope and a calibrated passive probe are connected to the output of the ripple checker while the X6417 is operating at full rated output. Output voltage is enabled, and ripple reading should appear in the oscilloscope. The peak-to-peak ripple voltage is measured. Ripple measurement should be less than 50 volts peak to peak. In this case, the ripple reading is 5.24 volts of output, which is within specification. Ripple value is recorded. Continuing with the test, we move to the safety circuits and slow start test. For this test, we will use the manual simulator, which will close the interlock via the interlock switch. As mentioned below, this fixture already has the interlock 270 ohm resistor installed such that when it closes the switch, only 12 volts are across the interlock relay. For this test, both filament and high voltage output will be confirmed to disable when the interlock is open and to enable when the interlock is closed. As you saw, filament and high voltage were disabled when the interlock was open. When closing the interlock again, filament and high voltage enable back. This cycling is repeated multiple times to confirm the reliability of the interlock circuit. After completing various cycles, the KV monitor signal is monitored using a calibrated oscilloscope and a calibrated passive probe to measure the slow start of the generator. Rise time of the output voltage monitor signal after closing the interlock should be approximately 2 seconds. As seen in the video, this is approximately 2 seconds. Value is recorded in the datasheet. The following tests are the filament limit and filament preheat range tests, using the adjustment potentiometers for filament preheat and filament limit. We will begin adjusting first the filament preheat pot between minimum and maximum value to ensure filament can be adjusted at least between 0.3 amperes and 1 ampere. In this case, as shown in the video, range should allow to adjust these values slightly lower than 0.3 amperes and slightly higher than 1 ampere in order to provide sufficient adjustment margin. This test is to be performed with the interlock open for the preheat to be active. We will then proceed to close the interlock and adjust the filament limit potentiometer between minimum and maximum. Values should be able to be adjusted between 0.5 amps and 1.8 amps. As with the preheat values, these are expected to be able to be adjusted slightly lower than 0.5 amps and slightly higher than 1.8 amps to provide adjustment margin. At this stage, after confirming the range, is where the filament presets will be carried. However, since X6417 does not have any preset specification, potentiometers would be set to minimum after the filament voltage limit test. For the filament voltage limit test, filament limit setting will be set at 1.8 amps, and then the filament load will be opened, measuring the voltage across the filament connector. Filament voltage should limit between 7.5 volts and 8.1 volts. We can observe that filament voltage with the filament connection open limits to 7.73 volts, which is within specification. Value is to be recorded in the datasheet. The next test to be carried is the operating frequency tests, where the inverter frequency is verified to confirm it is working within specification. This will be measured at TP9 with the unit providing full rated output. Frequency should be in the range of 30 kHz to 34.9 kHz. Measurements indicate that the frequency is at 31.53 kHz, which is within the specification. Value is recorded in the datasheet. As mentioned at the end of the filament test, We will exemplify how filament is preset for this model. Filament is preset to the minimum value as shown for both filament limit and filament preheat. In addition to the filament presets, output voltage and emission loop setpoint also have presets performed at the output voltage and the MA local control pots. This will be set to minimum for X60417. We will initiate by monitoring the current programming at the test fixture. This is directly connected to pin 10 in the 15-pin connector. You can notice is currently at the maximum value and will decrease this to the minimum, which is 0 volts. Also, we will monitor the output voltage programming test point in the fixture that is connected directly to pin 7 of the 15-pin connector. You will see that programming voltage as well as output voltage are at max rated value, since the output is at 50 kV. Potentiometer will be decreased to minimum, which is 0 volts. Presets will be recorded in the datasheet. In addition, filament monitor accuracy is the following to be reviewed. We will set the filament limit value to 1.8 amps plus minus 0.03 amps. Filament limit value should be in the range of 1.746 volts to 1.845 volts. In this case, monitor value is 1.80 volts, which is within specification. Filament is then returned to the minimum preset value. The next step is to perform the computer interface test. The computer interface test verifies the operation of the Micro X6417 with the serial, USB, and Ethernet interfaces through the Spelman GUI. In order to perform this communication, computer is connected through these interfaces while the fixture that was connected to the 15-pin connector is replaced by a jumper that contains only the interlock setting and key monitor signals that will be reviewed during the test. As shown in the screen, this is the Spelman GUI or graphic user interface. As mentioned before and as shown in the drop-down menu, this has the capability of connecting through serial, USB, or Ethernet communication. It should be noticed that besides being connected through this interfaces, it is necessary to have the DIP switch identified as SW1 in the configuration shown in the screen. as this will tie the analog outputs of the processor being used for the digital communication to the micro X control signals. It can also be shown that, as mentioned in the previous schematics, a jumper connected to the 15-pin connector that still has the 270 ohm resistor in series with the interlock connection is used. Another information to remember is that, before connecting through the Ethernet protocol to the X6471, user must ensure that the computer's IP address is configured to 192.168.1 and other 3 numbers. After ensuring all configuration is correct, we will proceed to connect through the serial port, selecting the desired COM port, baud rate, and parity settings. After clicking Connect, the GUI will turn the connection indicator to green and will report no faults. The GUI has 4 main screens, the first one being the home page where the output voltage and emission loop settings are configured. The next screen is the filament status window, where filament preheat and filament limit settings are configured and monitored. After that, we have the configuration window, which contains the connection status and firmware revision numbers. And last there is the diagnostics window, which contains fault status information as well as multiplier and control temperature and input voltage data. Before proceeding with the computer interface test, we will also present a reminder of the access to the factory settings, which can be accessed by Alt plus double-click on the high voltage logo and entering the password. Once open, factory settings will appear. These contain information such as scaling factors for the GUI monitor signals, the model number and revision for the X6417, among other information, but being the most important, the filament and preheat limits and the power limitation. 4X6417 power limit is set at 100 watts and filament limit is set to 1.9 amps. Filament preheat to 1 amp. These are newly revised values we will be loadings, since per discussions with New York Engineering, further adjustment margins need to be provided to account for X-ray tube tolerances. We will begin the computer interface test by programming values at half scale for the output voltage and emission current. In this case, this will be 25 kilovolts and 1 milliamp. You will notice that since the interlock is turned off, the readback values are not displaying anything since there is no output. This can also be confirmed by the output meter readings. We can also confirm that DS1 LED in the multiplier is off. We will now proceed to program filament preheat and filament limit values. Filament limit will be programmed to 1.8 amps and filament preheat will be set to 1 amp. You will notice that since the interlock is turned off, the filament preheat control is dominating and only the preheat current is available. We will now proceed to turn the interlock on, which will result in the unit providing high voltage output as well as going to max filament limit current. Values obtained in the GUI will be compared to the readings from the DMM. Values from the GUI readbacks are to be listed in the datasheet. Also, the change in DS1 status should be reviewed. After this has been confirmed, we will reset all settings, turn off the interlock, and then disconnect. Tests should be repeated for the USB connection. As seen in the screen test result for USB, are also successful and GUI readbacks are compared to the actual output readings. These will also be recorded in the datasheet. Settings are reset to 0 again, and configuration is carried through the Ethernet communication now, performing the exact same tests that were performed for the RS-232 and the USB connections. Something that needs to be mentioned is that the MA readback does not appear during this test, as mentioned in the current accuracy verification steps. The current readback or monitors will not be available unless operation with X-Ray 2 is performed. Values will be taken once during that test. The following test to be performed is the self-diagnostics test, which will be carried mostly in interaction with this screen, which contains all the fault information and general operating conditions of the unit, such as input voltage and temperature. We will be testing for the over-voltage protection fault, the interlock fault, the overpower fault, and the under-voltage fault. Testing will start with the over-voltage protection fault, for which an external power supply will be used to inject programming voltage into the voltage programming line. Before proceeding with the test, It must be noted that switch 1 position 1 must be in the off position to isolate the processor I/O from the supply voltage. We will then connect the power supply from ground to TP7. Once in position, we will begin increasing the programming voltage slowly to 10 volts. You will notice the output voltage as well as the readback indicator begins to increase while the set point remains at 0V. Once reached, continue increasing until the unit shuts down. Record the voltage during shutdown. It should be equal or less to 6% above the rated voltage, which in this case occurred without issues. We will also confirm that the high voltage on LED turned off and that the power on LED is blinking. There also should be no output present, and the over voltage fault indicator in the GUI should be on. It can also be noticed that even when attempting to turn on the interlock, without cleaning, the faults will yield in the unit not responding. Click Clear Faults. Operation should re-establish back to normal. Confirming for a second time at a slower rate of increase. It is still confirmed that the X6417 faults at 10.6V. Dip switch is converted back to normal for the next test, which is essentially the overpower fault. In order to perform the overpower fault test, voltage monitor and MA monitor need to be present. This will be achieved by adding a jumper JP2 to the control PCB. After that, factory settings menu need to be accessed to change the power limitation to 25 watts. In order to do so, change power limit to 25 and click Save Config. Turn on the interlock and program 1 milliamp of current. Attempt to program 50 kV. You will notice that power limitation will not allow for that, issuing a red flash in the kV setpoint window. On the contrary, it will allow the system to program 25 kV due to the 25 watt limitation. After confirming this, set the MOS setpoint to 0V and change the kV setpoint to 50 kV. Readback readings will exceed the 25 watt setting, issuing an over power limit fault. Check on datasheet. Remove JP2. Also return factory settings to the previous value. We will now perform the interlock fault test. We will close the interlock after clearing the faults. Then, with the unit operating, we will proceed to remove the interlock connector from the 15-pin connector. High voltage on LED should turn off and power on LED should be blinking. The GUI will also issue an interlock fault and will also indicate open interlock. It must be noted that even after clearing the fault, if the interlock is not placed back at the 15-pin connector, it will not allow to enable the high voltage on signal. Lastly, we will conclude the self-diagnostic test with the undervoltage fault test. With the unit powered off, we will proceed to close the interlock and then begin decreasing the power supply voltage until an undervoltage fault is issued. As with other faults, power on LED should be blinking and high voltage on LED should be off. Undervoltage fault should be issued at 18V plus minus 2V. It can be seen that undervoltage fault occurs at 17.9 volts. At the 15-pin interface jumper, there are two signals of interest we will monitor. One of these is a 24V monitor signal that is located at the pin 13 of the 15-pin connector. Using the test point DMM, we will measure the pin labeled as 25V. This should be approximately 24V. After confirming value is 24V, we will proceed to test for the open collector interlock feedback signal. This tests the activation of a MOSFET output that is located at the pin 12 of the 15-pin connector. Signal will be open or off when the interlock is open and will show closed or on when the interlock is closed. Using a DMM in ohms, meter is connected to pin 12 and measuring the resistance across those terminals to confirm operation. In this case, signal is operating successfully. Result to be noted in datasheet. Before proceeding to tube test, we will ensure that tube current sense resistor R178 has been installed. This can be done by performing the measurement between the cathode of CR20 and between CR41 and CR49. Resistance should measure 2.49 kilo ohms. Readings indicate that resistor is present and is the correct value. Point is to be checked off in datasheet. The final step of the test process is the testing with X-ray tube. In this case, we're using the same test setup as for the computer interface test, with the exception that we are using a Petric X-ray tube. You will be able to notice that we have a T-type thermocouple attached to the housing of the tube assembly near the anode section to monitor that the temperature does not exceed 30 degrees Celsius. We also have a radiation meter to monitor radiation leakage. In addition, an oscilloscope will be used to monitor the emission current and the output voltage at the pins 3 and 2 of the 15-pin connector. We will initiate by programming filament limit settings and filament preheat settings. Filament limit will be set slightly higher than 1.8 amps, per the recommendation of New York Engineering to allow margin for different tube tolerances, given that this is a 2 amps tube. Interlock will be closed, and then we will begin testing at 30 kV, 300 microamp. Once output has stabilized, we will continue to increase output voltage until reaching 50 kilovolts. Upon reaching 50 kilovolts, we will continue to increase emission current until 2 milliamps are reached. Constant checking of the tube temperature should occur during this test. Once 2 milliamps are reached, the voltage and current monitors will be reviewed for stability in the oscilloscope. Changing the time per division, setting down to 400 microseconds per division to ensure no abnormalities. Tube will continue to be left operating to look for any abnormalities. Interlock will also be opened and closed to confirm filament and emission current ramp at approximately the same time and oscillations do not occur. Once X-ray tube temperature has reached 30 degrees Celsius, interlock will be opened to shut down operation. Interlock status LED in the multiplier will be reviewed, and multiplier and control temperature values from the diagnostic screen will be recorded in the test datasheet. Before proceeding to check off datasheet and move the unit to final inspection, MAC address and firmware need to be recorded. In order to get access to the MAC address, type the unit's IP address in the web browse. The following page will appear where access under username admin and password SHV will provide permissions to get to the network settings menu, where the MAC address can be obtained. In addition, DSP firmware number and GUI number can be obtained from the communication screen in the GUI. Record these in the datasheet. This concludes the final test video demonstration.